the Linux kernel, every type of socket has a set of functions, pointers associated with it called proto-ops, which stands for protocol operations. And those protocol operations, they implement the various operations that can be performed on a socket. So it can be accept, bind, shutdown, etc. And thanks to this, the general socket management code doesn't have to know about the underlying transport or protocol because everything is abstracted away. So that's quite convenient, and you can see here the proto-ops definition as available in include/linux/net.h. So you see a struct proto-ops with different operations: release, bind, accept, and so basically what drivers do is they implement the operation they support, and they point to they implement the operation they support, and they point to operation they don't support to predefined kernel stubs. So in this illustration, you see, for instance, release points to my release, which is an implementation, bind to my bind, but accept points to sock no accept, which basically means this is an unimplemented operation. So this model is really fragile if you think about it, because anytime you add a new operations on sockets, what do you need to do? You need to update all drivers and point the new operation to a stub or implement it. And it's actually a lot of code to update because it means all drivers, right? And on Linux, it's a lot of drivers. And also, since macros are used for initializations, you also need to update all those macros. So, of course, it went wrong. And when success page was added, so success page is quite old. I think it was added in Linux 2.2 actually. Well, anyway, so when success page was added, it assumed the corresponding proto-ops field will always be correctly initialized. And well, that was not a good assumption. So you can see here the code from success page, and if you read the very bottom line, it just returns sock ops send page without checking that this is not null. So of course it went wrong, and it went very wrong because first a lot of drivers did not get properly updated. But the really funny thing that we found out was that the very sockops wrap macro, which is used to initialize a lot of drivers, had a bug. And the bug is quite subtle. I mean, if you want to take a look, it's not trivial to spot, I would say, because the macro itself uses a lot of other macros. It's a mess. So basically what happened is, for many drivers, even those which had been updated, send page was implicitly initialized to null. So, well, success page would happily start executing code at null for you. So the exploitation was just you map your shellcode at null, you trigger send page, for instance, by using the send file system call, and you get your code executed. So we wrote a trivial exploit for this that we shared with vendors, and but other people have written public exploits for like pretty much every popular architecture. So you can find this easily online. Shortly after that, we found another one, which was, not as bad, but way more complicated. It was possible. We found out that it was possible to trigger a special code pass in UDP send message that would result in calling some function called IP append data with a null routing table. The interesting part of this bug is mostly that it's quite hard to spot. If you look at this function, the code path is really complicated. And this time it was a data null pointer dereference. The attacker would control some kernel data, a routing table, through address null, and this turned out to be exploitable as well, although it was less trivial. You want to talk about this one?
So another interesting Linux bug that we worked on was a use after free in the Linux f-async subsystem. So if a driver wants to provide asynchronous I/O notification, they have a linked list of f-async structs that contain the FDs and the corresponding file structures that they want to notify when I/O is available. The same file structure, it turns out the same file structure could be in multiple f-async struct lists, and there was a special one specifically for locked files. If the file was locked and then closed, there was a logical bug where the file structure would be removed from only the locked files linked list. The structure would be freed even though it appeared in multiple lists. So then you have this structure in the second list that's been released and is being passed out to anybody else who wants some k-malloc buffer. So the driver still had a reference to this freed file structure. So this was, we wrote a proof of concept, but we didn't get an exploit working simply because it was really, really complicated. But we released the information about it in Linux, and a guy called Gabriel Campana wrote an exploit for it. And he wrote an article in a French information security magazine called MISC, M-I-S-E. I don't read French, but I'm told from French speakers that it was actually an awesome article, so if you do read French, you should check it out. He used some really cool tricks to get it reliable and to make a reliable code execution. So yeah, you should check that out if you're interested.
So this bug is in NetBSD. It's the only NetBSD bug we are talking about today, but we really love this bug. Actually, investigating this bug took me more time than for a lot of other bugs we're talking about today. It was really nice. So we found out, well, I mean, it's documented in the Intel manuals, but it's not very easy to find, that an interprivileged IRET can fail before the privilege switch occurs. So what we called this the commit point where the privilege switch occurs. So we said IRET can fail pre-commit. So for instance, if the restored EIP is past the code segment limit, a general protection fault will occur while in kernel mode. So no privilege switch will occur. So what difference does it make that no privilege switch occurs? Well, if no privilege switch occurs, no stack switch occurs between userland and kernel-land stacks. So basically you have no saved stack information on the trap frame. So if your operating system is not expecting this, and NetBSD was not expecting this to happen, so it was expecting a full trap frame all the time, well, basically you will have your trap frame shifted. So of course you can play with this and try to exploit this. And so we were thinking about this, and we also found out that the way the non-executable stack emulation work on NetBSD is they put a code segment limit just below the stack. So we found out that during a legitimate program's execution we could trigger the bug, because if you happen to have legitimate code on the stack, so that happens for instance if you have nested functions in GCC, you can get a trampoline on the stack. So if you're for instance in a signal handler in the kernel and you return from the signal handler to this trampoline on the stack for a nested function, you will directly return from kernel to code that's actually past the segment limit. So that's exactly the situation we described here. And so what this means is this bug can actually happen like this in real life and just crash NetBSD kernels. So we reported this a long time ago, I think more a year and a half ago, and I think it's still not corrected as far as we know. That one was really interesting because actually Taviso used this trick later for his NTVDM exploit, which I think you're going to talk about now.
Okay, so after we discovered these fun bugs in various interrupt handlers, we decided this was going to be some fruitful research, so we decided to audit the remaining interrupt handlers we could find. So we found one section of code in KI trap OD, which is the name of the GP trap handler in Microsoft public symbols. And we found one location where it appeared to trust the contents of the trap frame. This was a bit of a WTF moment for us, where we saw this code that was obviously doing something completely bizarre. We could tell that this was a component of the virtual 8286 mode monitor, simply because the branch to reach this code was checking the VM flag in the eFlags image. So reaching this code was really hard work, and it took about 2 weeks of research to figure out how to reach this code. And on top of that, we needed to write a reliable exploit. But I think it was worth it. At the end, we found a really fascinating and ancient vulnerability in really the core of Windows NT. And yeah, I actually won a Pony Award for this last night, so I guess it was worth it. So this is a recap of some of the features that we needed to exploit this. If you can remember MS-DOS programming, you'll be familiar with int21, which is used to invoke system services. But if you wanted to make a BIOS call to interact with the hardware, then you needed to call other interrupt handlers. Most people remember int10 because it was used for things like the demo scene. So that one's quite famous. But obviously, you can't allow a protected mode task to interact with hardware this way. So in virtual 806 mode, these services are intercepted by the monitor. So Intel calls this concept sensitive instructions. So basically, what they do is any operation that a real mode program would expect to work is made sensitive, and that basically means that Intel will cause its GP and give the operating system a chance to fix this up or emulate it or do whatever it wants. So in this way, programs that could never be allowed to work in protected mode can all the services they expect to be able to use can be faked, and they can think they're working on a real MS-DOS system or whatever. So yeah, these actions trap, and then the kernel is given an opportunity to decide how it wants to proceed. So the design of the virtual 806 mode monitor in Windows NT has really never changed since its implementation in the early 90s. And in fact, yeah, if you download these old service packs from ftp.microsoft.com for old, out-of-date versions that they don't support, you can still get a copy of these kernels. They even include public symbols, but obviously they're in DBG format, not PDB like we use nowadays. But still, you can still parse them and look around. It's kind of archaeology for code, I guess. It's kind of fun. So yeah, in order to support these BIOS service routines, a stub exists in the GP trap handler that restores execution context for the trap frame. In order to access this code, it's authenticated, but these were by magic values that we already knew that we could forge from our VMware exploit and from our previous work on interrupt handlers. So we knew that we were onto something that we could really control. There were lots of hurdles on the way, and it took us a long time to reach this. But each one was an interesting exercise, and I'm going to talk a bit about them. So how do you interact with the virtual 806 mode monitor? On Windows NT, it's an undocumented system service called NT VDM control. It's authenticated. You're not allowed to access it unless you have a special flag in your eProcess structure called VDM allowed. You can't set this flag unless you have SE TCP privilege, and you'll use something like, I think it's NT set system information or set process information. And you need SE TCP privilege. So if you have SE TCP privilege, like TCP is trusted code base, then you're already one of the most privileged processes on the system, and you don't really need to escalate privileges any further. So it's not immediately obvious that you can still access this system call. But you can defeat this really easily. All you have to do is invoke the real NTVDM subsystem, and then use the Win32 API, create remote thread to execute within it. This way, your thread is executing within a process that already has this flag set in its eProcess structure. So yeah, NTVDM control is completely undocumented. The best documentation for it is really Alex Ionescu has already reverse engineered it, so you can work out the API from his code in React OS. So yeah, he's already done all the hard work, so it's you can understand it that way. There's still a lot of special cases that we needed to understand for this particular bug. We needed to bypass things like checks for structure sizes and magic checks and so on. It took some time. But yeah, Alex Ionescu's code in React OS was really how to understand this stuff. So this code that we'd found in the GP trap handler was guided by a test for a specific CS EIP pair. We can forge these with these trap frames by making IRET fail, but you can't request to return into an RG code segment. Obviously, that would be stupid because you're just using RPL0 value and